Hello and welcome to episode 4 in the series on GPU programming. The plan for this episode is to continue training our neural network that we created in the previous episode. So we will have to write a backward pass. And what a backward pass does is it changes each weight and bias in our neural network in a way that minimizes the loss function, and therefore improving our performance. But we cannot just change our weights and biases randomly until we get some good performance. Well, not if we want to find the optimum in a reasonable time anyway. And to solve this problem, we need to think about what we want to achieve. We have our loss function, and we want to take the weights and biases of our network and subtract the errors that make the loss higher. And the error can be specified as the derivative of the loss with respect to our weight. Remember that the derivative tells us how changing our weight will influence our loss, meaning that if our derivative is slightly positive, increasing our weight will make the loss go up, and decreasing it will make the loss go down. Now, there is a problem of how to calculate the derivative with respect to each weight. And it turns out that it's not as hard as you might expect. There is an amazing mathematical tool that allows us to do this with simple functions, and it's called the chain rule. It essentially says that when we know the error in the last layer, we can calculate the error in the weights of the layer before it by multiplying its influence on the activations by that error. That is why we call this backpropagation. We start by calculating the error at the end, and we go backwards, propagating the error through our network. To formalize, our first backpropagation equation would be that the error in the last layer is equal to the derivative of the loss with respect to the activations of the last layer times the derivative of the activation of the last layer with respect to the inputs of that layer. Let's start by calculating the error in the last layer of our neural network. And I do have to warn you, this will be the hardest part of this episode, but bear with me as it simplifies beautifully at the end. As a reminder, our final activation layer was using the Softmax function, and our loss function was the cross entropy loss. Let's start by calculating the derivative of the Softmax with respect to the inputs. Since each element of the Softmax function depends on all the other elements in the input, we have to expect the derivative to take the form of a matrix. To simplify calculating the derivative, we'll consult our new best friend, the chain rule, once again, using something called the log derivative trick. By rearranging the equation a little bit, we can transform our derivative of a softmax element into that element multiplied by a derivative of its logarithm. This will come in very handy when calculating the derivative of softmax, as it helps us remove the division operator, as well as the exponent. If we were to take a derivative of this with respect to an arbitrary input, the left-hand side would simplify to 1 if our element index matches the derivative index, and 0 otherwise. As for the right-hand side, we can go for the chain rule once again. We can take the sum outside of our derivative, and notice that the right-hand side of this depends on x only for one element. And the derivative of e to the power of x over x is e to the power of x. If we move it into our fraction, we can see that we arrived back into the softmax equation. We can now plug in all of the values and arrive with this matrix of softmax derivatives. I know that this has been a lot, so pause the video and look over all the components one more time to make sure that you understand where they all come from. To finish with our calculations, we have to calculate the derivative of our loss with respect to the activations. And it is the derivative of log of our softmax output times the true probability. We can do a vector matrix multiplication to get the derivative of our loss with respect to the inputs. Now remember, P is a probability distribution, so its sum will always be equal to 1. Simplifying even further, it turns out that the derivative of our loss with respect to the inputs is simply just a vector subtraction of the softmax outputs and the true distribution. And this is the kernel that we'll use to calculate it. I won't go into details on it, as you should be familiar with all the patterns used. Now that we have the first piece of the puzzle in place, let's look into how do we backpropagate through our layers. With the derivative of our loss with respect to the inputs of the output layer, we want to go a step back and calculate how the activations of the previous layer influenced our loss. And we can do that with the chain rule by multiplying our result by the derivative of the inputs to that layer with respect to the activations of the previous layer. Remember that our equation for the input to the next layers was a matrix multiplication with the weights and the activations of the previous layer. If we take a derivative of that, we arrive with just the weights of that layer. And this is the kernel that helps us achieve this. And it's simply performing a matrix multiplication of our weights and the error from the next layer. To finish our backpropagation, we now need to be able to backpropagate through a ReLU function. And it is simply just 1 if x is greater than 0, and 0 otherwise. In order to backpropagate that, we need to multiply everything by the result of our previous step. And that's it. When we add this kernel to our arsenal, we can stack them infinitely to backpropagate through as many layers as we want. The final piece of the puzzle will be calculating the amount of error in our weights and biases. We can do that by first using our expression for the output of a layer, and then taking its derivative with respect to the weights, as well as the biases. And by using our previously calculated derivative of the loss with respect to the outputs of that layer, as well as the chain rule, we can calculate the error in our weights and biases. To update our weights, we will use an algorithm called stochastic gradient descent. It just simply reduces our weights by the average error in our batch multiplied by a hyperparameter called learning rate that tunes how big of a step in the optimization space we will be taking. And this is exactly what our last kernel will do. It calculates the error in our weights and biases and updates them with stochastic gradient descent. And this will be it for our simple neural network. I'll leave a link in the description to the full code so that you can read it and play around with it on your own. Subscribe if you don't want to miss the next one, where we will start diving into getting all of the performance we can out of our GPUs. Also, leave a thumbs up if you liked the video and share it with your friends. It helps me grow the channel. Thank you for your support, and see you in the next one. Bye.